Welcome to today's AMS-MAA invited address, where we're going to learn about detecting shenanigans in lotteries. It's my pleasure to introduce the speaker, Skip Garibaldi. Let me breeze through his background. He got an undergraduate degree at Purdue, a graduate degree at the University of California at San Diego. After that, he went to, I guess, a postdoc. Skip's here at Zurich. Yes. Followed by teaching at UCLA and teaching at Emory University, where he had a distinguished research professorship. In 2013, he was appointed to be Associate Director at the Institute of Pure and Applied Mathematics at the campus of UCLA. He is currently the Director of IDA's Center for Communications Research in San Diego. Most of Skip's academic research is in the general area of algebraic groups. He seems to have a special fixation on the exceptional group, E8. Some of his many publications include a monograph of Mercury Evans Sayre on cohomological invariance in Galois cohomology, a relatively recent survey article in the AMS on his E8 fixation, and he wrote an article on lotteries a while ago for which he won the Lester R. Ford MAA award. That was one of his many awards. Let's see, he's an avid and talented climber. He's climbed El Capitan, and I know that he brought ropes along because I think he was roped to the cliff face, on that climb or other climbs. I don't absolutely know that he used the ropes, but at least he had them. After all of that, I should tell you, you now know the answer to the crossword clue number 43 on the MAA's crossword contest today. The contest is due at noon, so you might be able to dash out and exploit that information, except that I think you're going to be glued to your seat by an absolutely fascinating talk, so you're not going to be able to actually use that information. Anyway, it's my pleasure to introduce Skip. Let's welcome him.
Thank you very much, Joe. So I got to get a copy of this crossword. I do crosswords every day, this is like a fantasy of mine come true. I hope someone at the MAA is saving me a copy. All right, so before we get started, I'm from IDA. Most of their speakers are professors, faculty. You kind of know what their job's like. Many of you don't know about IDA, but it's around. And in particular, we're a nonprofit that does math research in the interest of national security. You may have seen some recent articles in the notices by IDA staff members. On the left, you have an article from October by Kelly Yancey. She works at not my site, but our Maryland office. We also have a Princeton office. The middle article is one that I wrote in the current print issue of the notices. And if you want to find out more about IDA and our paid summer research program for mathematicians and people in mathematically related disciplines, you can come to the big career center this afternoon. But I'm talking today about work that I started when I was at UCLA, and I'm going to talk about the lottery. So the lottery is huge business. Lottery ticket sales in the US are about $80 billion per year. And I know it's a huge number. It's hard to wrap your mind around. So here are some comparisons in case those are helpful. That's 10 times the NBA's global revenue. And the NBA is clearly big business, so lottery sales even bigger. It's twice Microsoft's global revenue. And it's about what the US spends on corrections, which includes prisons, jails, parole officers, and so on. So it's a huge amount of money. And so what I'm going to talk about today are some shenanigans that are widespread, ongoing, and in many cases illegal. The details about whether it's illegal or not depends on the minutia of state law. So it's different from place to place. And those are some important points. The reason I want to highlight these is because there are lots of shenanigans going on in the lottery. A huge array. 2 weeks ago, some woman was arrested because she bought a used car using a forged winning lottery ticket. That's not what I'm talking about. Here are some other things I'm not talking about. I'm not talking about every mathematician's most well-known lottery shenanigan, Massachusetts cash windfall. This is a specific game that happened to have a positive rate of return between 2005 and 2012 in certain drawings, and so some people exploited that. I'm not talking about that because that was in a specific place for a specific time, and it was totally legal. But if you want to learn more, you can read about it in a bunch of places. My reference I gave here is Jordan Ellenberg's book, because that's a great book. You should read it anyway, but that chapter is on this subject. There's also inside jobs. I'm not talking about those. Those are great crime stories, super fun to talk about, but there's not a lot of math involved in uncovering the inside jobs. So a couple of those stories that you may have seen recently, Eddie Tipton just went to jail for rigging some multi-state drawings by adjusting the pseudo-random number generator used to pick the winning numbers. There was a different but similar scheme in 1980 in Pennsylvania that's in the movie Lucky Numbers, starring John Travolta and Lisa Kudrow. If you're interested. There's this thing where sometimes long ago, the company that makes the scratcher tickets makes some mistake, and if you know how to look at this ticket right, you can figure out before you buy it whether it's a winner or not. That's a thing, but it's legal. It's only happened for specific poorly designed games in very specific locations, and the scratcher manufacturers are smart. They probably don't do that anymore. So I'm not going to talk about that either. There's a lot of stories about the luckiest woman on earth, Joanne Ginther. She has a PhD in stat ed from Stanford. It comes up a lot in newspaper articles. I don't know what she's doing. She's doing something. It might just be a gambling strategy. It might be 100% legal, and she might be just pursuing some strategy. I don't know what that is. If anyone's interested, has some theories about what she's doing, I'd love to talk about it. It's a thing I've been thinking about for a while, and I would like to happy to talk about with other people. All right, so I'm not talking about those things or many other shenanigans. I'm talking about a specific thing. So how did this story start? This guy, Lawrence Maurer, he's an investigative reporter. At the time, he worked for the Palm Beach Post, which is a print newspaper. This happened a few years ago, but even then, that felt like a real anachronism. So his job is amazing. His job is to find an interesting news story, spend 4 to 6 months researching it, and then write some newspaper articles about it. It's really a great gig if your dream is to be a journalist. And so he was always on the look for new stories. And because he was in Florida, he thought to himself, well, hey, maybe there's something up with the Florida lottery. He'd read an article about one of these other shenanigans and had some ideas. So that was his question. And so what he did was, by the way, you might have noticed the masthead for the Palm Beach Post over there. Real news starts here. Nowadays, you maybe don't even notice that phrase, but that masthead predates the whole fake news thing. And so whoever came up with that slogan looks really prescient as of a couple years ago. All right, so he wants to investigate what's going on with the lottery, just to see if there's a story there. And so he went and got some data. And the data he got was a list of more than 1 million prizes given out in the Florida lottery worth $600 or more. At the time he got the data, this was the complete list of such prizes that had been given out. And it's just a big Excel spreadsheet with a lot of rows. And for each win, he knows the winner's name, the winner's city, what game they played, how much they won, where the ticket was bought, that kind of information. So I should say a few words about why we have that much information. So as many of you know from having bought lottery tickets yourself, if you win a small prize, like $1 or $10, you can just bring it to your nearest grocery store or gas station or whatever, and they will take your ticket and give you money. Super easy. Those kinds of wins are not really tracked. But if you win a big prize, in Florida, the definition of big is $600 or more. That's the same rule that Colorado uses and that California uses, by the way. But it varies from state to state. Then you have to go to a lottery office. There's only a few of them in each state. They're open Monday through Friday during business hours. And you have to fill out a form which asks for a lot of personal information, like your social security number, your birthday, and so on. And they do a lot of things, like they withhold taxes. And if you owe back child support, they'll take that out of your winnings and stuff like that. So those wins, the $600 or more wins claimed at lottery offices, are well recorded, and that's what we have data on. Now, whenever I give this talk, I like to ask the audience, has anyone here ever won in a Mega Millions, Fantasy 5, Super Lotto, some kind of state lottery, a prize worth $600 or more? Can I get a hand? I got 1. Okay, thank you. Awesome. So this conference has what, like 6,300 people at it? Anyone who likes the lottery is probably at my talk. I got 1 person. So that's my point. That's, by the way, the second person to ever raise their hand when I've given this talk. And I've given this talk to hundreds and hundreds of people. So the upshot of that is you should take away, we have just done a random sample, well, a somewhat random sample of the population. And what we can conclude is it's like super rare to have won one of these prizes, right? We've just seen it. And you've also just seen a bold mathematician doing crowd work, right, with a big audience, as you'll see that very often. Okay, so what he saw was something weird. Several people, like 10, had won more than 100 of these prizes. Well, that was surprising, right? I mean, so one question you might ask is, well, maybe our intuition is just bad. And that there are people out there who are spending so much on lottery tickets that you might just expect that to happen. Maybe even though our gut's saying, oh, that's too many big prizes, it's actually normal. Let's use some math to find out. That's the next slide. So it turns out we don't know too much about how much people spend on lottery tickets as individuals. Social scientists are very curious about that because people are curious about things like social costs of the lottery and what socioeconomic things are tied to purchasing lottery tickets. There's been a lot of surveys, and you can get survey data from the usual social science survey data repositories. What I've graphed here for you is a histogram of responses for one such survey, average monthly spending by individuals on lottery tickets. And what you can see quite clearly is that this data is very heavy-tailed. So there's like half the population, some large fraction of respondents, they pay $0 on lottery tickets every month. But way out on the right-hand side, you see that there's someone spending $2,000 a month on lottery tickets. So it's clearly heavy-tailed. And if you want to model this to try to answer the question, is it weird that so many people have so many big prizes, you really need to model that tail behavior. And we have precious little information about that tail. In the social science literature, you can find claims like this one, which is in one of the gold standards of social science literature on the lottery. 50% of the money spent on lottery tickets is spent by the heaviest 10% of players. Now, the roundness of those numbers should make you suspicious, by the way. And it turns out that I did a project with some 3 statistics undergrads at UCLA where we showed using various statistical methods that that is not even true to one significant figure. So that's not so good. So what that point of that is, we're not going to model that distribution. Now, we have a paper, you can read the paper and so on, and it contradicts a claim that was well accepted in the social science literature. But realistically, if we just sit back as normal people, we can see that we don't need fancy statistics to know that we're not going to be able to model that heavy tail. And let me explain why. It turns out that modeling heavy tail distributions, especially the tail behavior, is very hard to try to get a parametric model for that. You need a lot of data. It needs to be accurate data. And if you just think about how we're going to get data, someone's going to call someone on the phone and ask them how much they spent in the last month on lottery tickets. So suppose you get one of these heavy spenders, which you're not going to do because they're a very small fraction of the population. So suppose you get one of the heavy spenders and you ask them, and they try to be honest with you. What are the odds that they're even going to tell you the right number, no matter how hard they try? Who keeps that accurate of records? So we're not going to get good data about the tail. We're not going to be able to model it. Okay, so we can't answer the question in that way. So Lawrence, actually, he went to the Florida Lottery Secretary. When you hear that job title, you should think CEO of the Florida Lottery. That's her job, or was her job at the time. So she said, that's what the lottery's all about. You can buy one ticket and become a millionaire. She said, these gamblers are just lucky. And that's how come they won so many prizes. And so Lawrence found this intellectually challenging. So let me present to you the paradox that Lawrence faced. So on the one hand, we have the lottery secretary. She says, look, hypothetically speaking, that person could have bought exactly 100 tickets and gotten a big prize on every single one. Now, in this audience, we find that argument more convincing than most people. Let me just point that out. Because most of you in this audience can calculate. If I tell you they bought a ticket in this game and here are the rules of that game and here's the probability of winning, you can calculate the probability that they won. And then if they did 100 such things, you can multiply those probabilities and you can calculate the probability. And it is a non-zero number, right? So fundamentally speaking, in the pure math sense of the word, what she said could be true for some definition of could be. Now, on the other hand, Lawrence, he's not a mathematician, but his gut apparently has a really good understanding of binomial distributions. And he was like, yeah, but come on, right? So he has this fundamental philosophical, mathematical problem. And so he thinks to himself, I'm going to need professional help. And so he called in some mathematicians. So he called me and he called Philip Stark. Where's Philip? There he is. So this picture, by the way, was taken about an hour ago in the special session on securing elections that happened this morning. I hope you went to it. It was fantastic. So Philip is a statistician at UC Berkeley and associate dean. I have no idea how Lawrence found him. I think he found me because he probably Googled mathematician and lottery. And he called other people too, but we were the team. And Richard Aradia down here is a probabilist at USC, so we drug him into the whole thing, and the four of us worked together. All right, so our job now, just to recall, is to resolve this dichotomy, this dilemma between, this non-zero probability and, come on, that non-zero thing is just too small to be a thing. All right, so that's our task in front of us. So let's talk about what does it mean to be too small as a probability. It turns out this has been a long-running discussion in sort of popular probability literature. So there's a little potted history for you. The Comte de Buffon, who you know from Buffon's needle problem, he liked the 1 in 10,000 cutoff. He said if the probability is lower than that, then maybe we pretend that that thing's not going to happen. Marquis de Condorcet, you know about him from the voting paradox, about how if you have more than 2 options. Anyway, so he has some examples that are informative about that. So his cutoff was 1 in 144,768. Which is a weird number, right? So his reasoning, though, is pretty interesting. He said, when he was writing his book, he said, look, if you book a commercial passage across the English Channel, you don't make up your will as a special thing because you're worried you're going to die. You treat the probability of dying in that passage as not going to happen to you. And at the time, that was the chance of dying in such a passage. He gave another example too. He looked up in actuarial tables at the time, and he observed that that is also about the probability that a man between the ages of 37 and 47 would die during the next week. So those are 2 reasons, and again, we don't live our lives as if we're going to die in the next week, so that's a negligible probability for him. And then finally, Emile Borel, famous probabilist, you know him from Borel sets and Borel measure and so on. And he was briefly the French version of Secretary of the Navy, which is an interesting career turn for a mathematician. They say in Littlewood, from Hardy and Littlewood, they both argued for 1 in a million. And by similar reasoning, that we live, if the probability is less than that, then we live our lives as if it's not going to happen. So it's really an argument based on how humans behave, what the probability cutoff should be. So what we're going to use is we're going to use the most conservative number, the 1 in a million number. And the reason for that is you got to imagine how this is all going to play out. We're going to analyze this list of frequent winners. And probably we're going to deduce that some of them might be up to something. And Lawrence is going to go physically to their house, maybe with a camera crew, and he's going to ask them some pointed questions. And that's not going to be fun for them. So just in the interest of being nice to those people, the people we're suspicious of, we're going to give them the benefit of a doubt. Every time we have a design decision to make, we're going to take the conservative choice, the choice that makes them look more innocent. And so that's why we're going to take the 1 in a million bound here. All right. So great, so we've got our problem set up. This now sounds like a straight up binomial distribution problem. How much would a gambler have to spend on lottery tickets to have a probability of 1 in a million of winning so much? No, that is not the question we should ask. So I should point out that that question, phrased that way, is what many newspaper reporters fall into a logical trap and ask that form of the question when there's some weird lottery coincidence, like someone wins more than $1 million prize, which does happen. And you can read this nice article by Diaconis and Mosteller where I explain why that's totally to be expected. So that's not the right question to ask. Let's talk about why it's not the right question to ask. Well, it's because of a famous thing in laboratory sciences. We're testing multiple hypotheses because we don't care if this specific person won so many prizes. We care if anyone won so many prizes. We need to make a discount for somehow all of the lottery players. They're all independent tests we're making. And I've given you an illustration from Lab Science here, which is this great XKCD comic, where they're doing a lab test to look for correlations between acne and colored jelly beans. And sure enough, if you test 20 different colors of jelly beans, one of them is going to have a p-value of less than 0.05. So the message here is that what you need to do is discount for how many people are gambling. Okay, so that's what we're going to do. Okay, so we're going to ask how much would each Floridian have to spend for there to be a non-negligible chance of any one of them winning so much? Again, these are Florida lottery games, so realistically, it's Floridians playing, and actually not even that many of them. But in typical states, about half the population buys lottery tickets, so we could use a smaller number here, but again, we're taking the most conservative choice. So what we're going to do is we take the population of Florida, which at the time was about 20 million. We take our 1 in a million number from Emile Borel, and we're going to look for a probability that's at least 1 in the product of those two things. That's called the Bonferroni correction. That's a very easy correction for multiple hypothesis testing to understand. It's very robust, and it's very conservative. Again, we're taking the most conservative choice. Now, you all look at that, and you're like, that is a small number. Let me give you an illustration to demonstrate how small that number is. So imagine that you and your friend somehow managed to have a complete list in your head of all the stars in the Milky Way. Okay, now that can't happen for a lot of reasons. One of them is we actually don't know how many stars are in the Milky Way up to a factor of 2 or something, but there's some estimates, so let's pretend with me. So your friend picks one, and you pick one, and you happen to pick the same one. That's actually way more likely than this probability. Okay, so this is really unlikely, is my point. Okay, so that's our plan. That's what we're going to ask. And so we can do a toy version of this. I think most of you in the audience could do this problem right now. So let's just go through it. So they're going to play some game. It costs C dollars per ticket, whatever that is. They're going to buy T tickets. We don't know what that is. And we ask, how many tickets do they have to buy so that the probability of winning so many times is at least that probability cutoff? Now, it's just a binomial distribution problem. Most of you in the audience could do that right now on the back of an envelope. You might need a calculator to evaluate that regularized beta function. So in particular, what I just said is true. Well, it's true for scratcher games. So here's a technicality about lottery games. Lottery games mostly come in 2 different flavors. One are scratcher tickets. This is a ticket. You buy it at the store. There's some stuff covered up with wax. You scrape it off. You find out if you're a winner or not. The way those work is the lottery prints out many, many of those tickets, and you're going to buy some small fraction of them. So you can just model that with the binomial distribution. Totally fine. Easy peasy. However, there's another kind of game, draw games. And so draw games work differently. There you buy a ticket, which is like laying a bet on the outcome of the next drawing. And then at a later time, the drawing happens, and you find out if you win or not. And so and then it happens again and again and again. And so if you want to get so many wins, you have to know what the optimal strategy is for such games. Do I bet 1 ticket per drawing for as many drawings as I need? Do I put 5 tickets per drawing? How do I do that? And so you need to know the optimal strategy on these games. And so that's a result of Richard Stong. It's very complicated and technical, so I'm not going to present it here. It's super clever, though. It's pretty awesome. All right, but it turns out that you can still bound his result, and so that's what we do. So let me work through a couple of examples. So here's one of a Mega Millions jackpot. So Mega Millions, it costs $2 a ticket. Probability of winning a jackpot is 1 in 303 million using the current rules. So suppose someone wins a jackpot. Now, if you naively come at this with a binomial distribution, you might go, oh, well, they must have spent $606 million. That's 303 million times $2. But of course they didn't, right? There's Mega Millions drawings a couple times a week. People do win them, and none of those people spent $606 million on tickets. So obviously this expected value naive estimate is terrible. Our estimate says $2. So of course they did have to buy a ticket, so it can't be any lower than that. And this is actually realistic for most people. A lot of people who win the jackpot, why couldn't you just win it with 1 ticket? How much different is that than 10 tickets? Okay. So here's another example. Here's one where someone gets lots of wins. So in this example, you pay $1 per ticket. Your probability of winning is 1 in 1667. This is an actual game you can play in Florida, by the way. It's very unpopular, but it exists. And so suppose someone wins 200 times. Well, our naive estimate of spending is just 200 times the 1667. That's $333,000 and change. The formula gives this other estimate, 185,000. That's a lower bound using our probability cutoff. Now, so what's going on here, why this is giving some much more effective answer is because we have a lot more data here and that we have 200 wins. There's some kind of law of large numbers phenomenon here where you do a trial a bunch of times, you expect it to be more like the expected distribution. That's what you should be thinking about. So a lot of wins, that sounds like it's going to be more like this example, right? That's the thing you should have in mind. Okay. So, but this one game thing is totally not what we see for actual gamblers. The actual gamblers that we're interested in, the ones who won hundreds of prizes, they played many, many games. They won in many, many games. It's not the one game situation. So what we're actually going to do is we're going to modify the problem on the previous slide to account for that. So what we do is we replace our single number t, number of tickets, with a vector where every coordinate is the number of tickets in that game. One coordinate in the vector per game. We have another vector c, which is the cost of a ticket in that game, because games come in all different costs, $1, $2, $5, up to $50. So we want to account for that. We're going to use total spending on lottery tickets as our metric. So this dot product c dot t, that's just the total amount spent on lottery tickets. And we want to find the minimum number so that the probability of winning so many times is non-negligible. So the only, I got a few things to point out here. The right-hand side there, it says epsilon now instead of 5 times 10 to the minus 14th. And that's because, well, we're going to actually use a smaller number derived from 5 times 10 to the negative 14th using Fisher's method. This is a way of combining independent results to get an omnibus result. So there's a really good, it's really easy, beautiful math. I recommend it. Push things over to a chi-square distribution. But I'm not going to talk about it here because it's very, for statisticians, this is a completely normal tool that we're using. And it's also more conservative than just taking 5 times 10 to the minus 14th, also, let me point out, besides also being intellectually better. Okay, so that's what we're going to do. Much like the previous slide, though, where it was just one game, there are hidden gotchas. So for example, implicitly here, in the probability there, the thing that's defining the set of values of t that we're optimizing over, I've had a product of probabilities for different games. So implicitly, I've asserted there that the outcomes of different games are independent, which works totally great for scratcher games. Totally doesn't work for draw games. So specifically, there's a very popular draw game called Cash 4, where you bet on an outcome of the next drawing, but there are different bets you can make corresponding to different tickets. So you can say, I'm going to spend $1, and I'm going to guess that the next number to come up is 1, 2, 3, 4. That's a bet. You can also spend $1 and bet the next number that comes up is some permutation of the digits 1, 2, 3, 4. That's called a 6-way box. Those are 2 different bets you can make on the same drawing. Those bets are clearly dependent. So this product there is not mathematically justified. Okay, so we have to do some things to adjust for that. We use the BKR inequality. Well, that kind of thing happens when you have a professional probabilist on your team. That was a conjecture in probability that was posed about 1980 and eventually proved around 1990. But it really applies directly to this situation. It gives a very clean argument about why we can use a product there. Oh, and there's another hidden gotcha. So remembering back to your undergraduate multivariable calculus, you might look at that and think, hey, that is ripe for Lagrange multipliers. I'm going to crush this problem. But you're totally not going to do that because when you do multivariable calculus, there's always this miracle that you can solve for things in closed form. And you're not going to do it here because this probability is coming from the binomial distribution. So it's going to be given in terms of a regularized beta function. You can't solve that in a closed form way. So we're definitely going to use a computer for this. It's going to be a numerical optimization. And that's fine because it's super easy, but it introduces a hitch. The hitch is, well, as you know from Calc 1, when you optimize things on a computer, you find a local minimum. But we really need a global minimum here. Because remember, Lawrence has to travel to someplace in Florida. Florida's a pretty big state. He's going to show up at their house. He's going to ask some pointed questions. We don't want him to misfire. We need to make sure that's a global minimum. So to make sure it's a global minimum, we need to know something here. So the function you're optimizing, this dot product, is easy. It's a plane. That's the easiest thing to optimize over. What we need to know is that the feasible set, the values of t satisfying the probability constraint, is a convex set. And the standard technique when your thing is a product is to know that the things you're multiplying together are log concave. So I knew that's what I wanted. I'm no fool. I've taken convex optimization. So I go out looking. Turns out there's a lot of results in the literature on probability about concavity of functions like the regularized beta function. But for regularized beta, it's all in terms of the other parameters. And I was like, oh crud, do I have to prove something about special functions? And so I called this guy Karp, well, I emailed this guy, Dmitry Karp, who knows about special functions, and as I discovered by looking at the archive, and I said, hey, is this true? And he goes, well, I can prove it. And so he wrote this paper. And it's a really pretty paper. And then later on, we discovered that it's actually in the literature already, but I like Dmitry's proof better, so that's the reference I've given at the bottom of the slide. So it is, in fact, log concave in the right variable, and it took some work to even find that result. All right. So we did it. We set up the problem. We can plug it into a computer. It's now a numerical calculation you can do on your laptop with SciPy, MATLAB, whatever you want to do. And so we're going to apply it in Florida. What happened? OK, so let's talk about this is my favorite example, the guy from Pompano Beach. So he had a lot of wins, 252 wins worth $600 or more. So then we have the complete list of his wins and the rules of those games. Florida is pretty good about posting the rules for its lottery games, which was very helpful in this. And so we apply our method, and we found out he spent at least $2 million using our very conservative estimate. Now, in the lottery, $2 million doesn't sound like a lot of money. You're used to hearing things about like billion-dollar jackpots. So what's $2 million? It doesn't mean anything. So let me rephrase this number in a way to make it more impactful. He would have had to spend $1,000 a day on lottery tickets during the time when he was operating. Now that number should be shocking. So let me explain. If you want to spend $1,000 a day on lottery tickets, it is not easy. That's like a job. You gotta go to a store, they gotta have enough lottery tickets to sell you. You have to buy those tickets, and probably you want tickets in a specific game, so you gotta get the right store, and maybe you have to go to multiple stores. And then you have to get the tickets, and you have to scratch the tickets, and you have to find out if those tickets are winners. It's a job. Maybe you're skeptical. If you're skeptical, I would encourage you to do an experiment, to spend $1,000 a day on lottery tickets for a week, and come back and tell me how you found it. Okay, that's my question for you. So it's just physically hard to do it. So it seems a little suspicious, right? Now, don't get me wrong, I'm sure there are people out here who do that, but it's rare. And so now it's time for Lawrence to do a little shoe leather. And so part of the point of saying this is that our estimate is very conservative. So the odds of being both one of the very few people who spend so much on lottery tickets and also having gotten so very lucky that our conservative estimate only is that we won so many times, is unlikely. All right, in an imprecise gut sense, not in a precise mathematical sense. Okay, so Lawrence went and talked to this guy. Oh, sorry, I should explain. I should say, how could it have happened that you could win so many times without actually buying lottery tickets? Because there's lots and lots of schemes that will let you do this. So let me try to explain some of those schemes. So one of them is called pin scratching. And so the way it works is this. If you take I have a scratcher ticket up here on the screen as an illustration, you'll notice there's a barcode down there in the middle, and that barcode is covered up with wax when you buy the ticket. Now, when you go to cash in your lottery ticket that you think is a winner, the clerk is not going to look at your ticket and try to decipher it, because it turns out that's easy to screw up. I've screwed it up. I have a PhD in mathematics, and I've misread lottery tickets. So what the clerk does is they scan this barcode, and the computer tells them if it's a winner or not. All right, so in the scheme, that's what happens in the real world in normal, everyday, honest behavior. In the scam, the clerk is in the store, there's no one else around, they take a lottery ticket off the roll, they scratch very carefully the wax over the barcode, they scan it, if the ticket's a winner, they buy it and claim it as a prize for themselves and recorded it as the winner. And if it's a loser, they sell it to the next drunk person who walks in. So in this way, you can burn through a bunch of lottery tickets and only claim winners. And that way, a gas station clerk can amass a lot of wins. This is not such a popular scam anymore, ever since they went to two-dimensional barcodes like you see here. But in the old days, there were one-dimensional barcodes, and it was more popular. I've seen news stories about one person being arrested for this for the last few years, each year. So it's a pretty low-frequency scam these days. Another one is that clerks can steal winning tickets from gamblers. And this is a little complicated to explain, but it's a much more common scheme, and it happens all the time. So in this scheme, you've got some winning lottery tickets. The gambler has some winning lottery tickets, and they come into the store and they want to turn them in. They want the money for them. And they hand them over to the clerk, and the clerk says, okay, here's your money. And they give you the wrong amount of money. So typical example is you've got a $1,000 winner, and they give you $10. Or another variant is the clerk says, oh, I'm sorry, you're mistaken. This ticket's actually a loser. Let me just throw that away for you. Because people do make that mistake all the time, like I said. It's really easy to misread the ticket. And so it turns out that clerks actually do this, they totally do this, and then they take the winning ticket, the one that they scammed, and they take it to the lottery office and get counted as the winner. So that's another way to amass a lot of winners. And so that happens. Lotteries run sting operations to catch clerks who do this. It's a thing. Okay, another thing that they can do is buy winning tickets from actual gamblers. This is we call it ticket aggregation. It's sometimes called discounting. So the way this works is, it turns out that there's lots of reasons you might own a winning ticket and not want to go to the lottery office to turn it in. If you have a warrant out for your arrest, you might not be super excited to go into a government office and show photo ID. For example, if you owe back child support, the lottery is going to garnish that from your winnings. If you're a drug addict, you may want that money right away. So those are and the lottery office is only open Monday through Friday. You have to get a check. It takes you to a bank. It's very inconvenient. I know that sounds a little offhand or something or flippant, but that's totally the actual target audience for ticket aggregators. The drug addicts are their best customers because what happens is the gambler who has the ticket sells it to the aggregator, the middle person. The middle person pays them for it. So a $1,000 ticket, the gambler gets less than $1,000, right? Because the aggregator has to cover their income tax, their hassle to go to the lottery office, and so on, and the fact that what they're doing is actually illegal in many states. So if you're a drug addict, the going market rate in Florida for a $1,000 ticket is $200 to $300. Yeah, you're getting hosed, right? That's definitely exploitation. Okay, so that's the business. And also, another side aspect of this ticket aggregation, and I underline that because when I've described ticket aggregation in other talks, sometimes people react and say, oh, what's so bad about that? That's just a little bit of harmless tax evasion. Like, it's a little more nefarious than that. So here's another thing, money laundering. So as you know from watching Breaking Bad, if you have a criminal enterprise, you will amass large amounts of dirty cash. And what you'd like to do is get that into the banking system so that you can use it for normal money things like buying a house. All right, so you can use ticket aggregation as a vehicle for that because you pay the gambler with your dirty cash, and then you take the winning ticket to the lottery office and they give you a check, and that is money that is in the banking system. So that is laundering money at a profit, which I tell you gets organized crime very excited because money laundering is normally very expensive. So there have been various criminal syndicates that have been caught using ticket aggregation as a mechanism for laundering money. It's a thing. And so again, if you're one of the people who's saying, it's a bit of harmless tax evasion, I would just argue that the government should not be providing a vehicle for money laundering. That's just a thing we should not be supporting as a society. That's my personal view. You may disagree. Okay, so what happened with the guy from Pompano Beach? So in the first time Lawrence went to talk to him, he said, listen, I've never won. Someone is impersonating me and claiming prizes and using my name and personal information. But then the second time Lawrence talked to him, he just admitted. He said, yeah, I'm a ticket aggregator. That's just what I do. So we found someone. That's what they were doing. So it's great. So the math worked. Well, and I want to say that the math worked in a way that is even more than this. It's not just that we found someone who was up to something. we found something else interesting. There's this guy from Hollywood, Florida. I put the little pin on the map there so you don't get confused about which Hollywood it's in. There's this Hollywood guy who claimed an astounding 578 prizes. That's more than double what the guy from Pompano Beach claimed. And yet, our analysis suggested a much smaller number for amount wagered. And so we told Lawrence, we're like, hey, we don't know what the story is with this guy. He might just have a gambling problem, for example. And so Lawrence went and talked to him and talked to a bunch of other people in the neighborhood and so on, and he found out some stuff. So it turns out that, and I'm not going to go into the details because it's not very interesting, the particular game in Florida has these weird rules. So the number of wins listed in the spreadsheet is not the same as the number of wins that we should have included in our math. And so legitimately, the math analysis corresponds to only winning a handful of prizes. So he's much more like the Mega Millions example than the many wins example from the single game that I showed earlier. And furthermore, his gambling was really well documented in a variety of ways. So here's one story. Lawrence went to one of the stores where that guy allegedly bought many of his tickets. And he asked the clerks in that store, hey, do you know this guy who comes in here to buy lunch? Because they're like, oh yeah, we know that guy. And that's, which is what you expect to hear when someone's spending $1,000 a day on lottery tickets, say. Like, you're going to notice that person when they do that every day for multiple years, right? So, and just to really drive the nail home in this story, the clerk said, so the game he plays is one of those ones where you buy your ticket and there's a little printer that prints out your ticket. He was buying so many tickets that he was occupying that printer. So we, the store, had to buy a second printer just to print tickets for other customers. Right. So that's what I'm talking about when I say buying $1,000 with the lottery tickets a day is work, right? He affected the business operations at the stores where he purchased those tickets. So that's the kind of stories that Lawrence could have found. And that would have made the people that we thought were suspicious look innocent. But this is the only person that happened with. Okay, so you might ask, then what happened? So we did this math, we proved some theorems. By the way, now that the theorems are proved, it's just a calculus thing. Like in calculus class, first year calculus class, you do the inductive proof to prove the derivative of x to the n is n x to the n minus 1, and then after that you can just use the rule. It's the same thing here. There's all these gotchas in justifying that optimization problem as providing the useful number, but now that that theorem's proved, it's just an easy numerical calculation that you can put in a Jupyter notebook. So a lot of other places use that math to analyze the lottery results in those states. And so it happened across America. We've had some national studies. Georgia really took this message to heart, and they've been aggressively pursuing ticket aggregation. There was a court case about this just recently, and it was decided in the state's favor just 2 days ago. So it's pretty exciting. Stuff's still going on. Yeah. I should say, speaking now, not as someone who's interested in social good, but as a mathematician, Philip and I and Richard, we were really lucky that the first state that we started working on was Florida. Because Florida had enough shenanigans that we could detect them using math, but not enough that it was easy. Okay, so it's this beautiful, beautiful intersection. If it had been Georgia, which was the second state that we worked on, we would never have discovered all of this beautiful math because it turned out in Georgia that the problems were much more rampant. And so you didn't have to do any of these fancy techniques to find it. And most states are more like Florida. Anyway, Georgia's taken this issue very seriously though, and they've really taken a lot of steps to address it. So we had some changes. So the lottery, an easy thing for them to do to address ticket aggregation is just to stop ticket sales at stores they think are involved in scams. That's a really easy intervention for them to do, and they can do that right away. And up here in the upper right corner, you see a photograph there of lottery and law enforcement people taking all the lottery terminals out of one of the stores affiliated with the Pompano Beach man. So that's they just did that immediately. Another thing they do to stop the clerks stealing tickets from winning gamblers scam is they created more self-checking ticket terminals, it's hard for me to say, where you can scan your own barcode and see if you're a winner. And of course now there are smartphone apps for many states where you can scan your barcode yourself using your smartphone. Then there were changes in policy in multiple states to pursue ticket aggregators, including in Georgia. So like I said, they've really gone after it. There is Debbie Alford in the lower right corner. She is the CEO of the Georgia Lottery at the time our story broke. She just stepped down recently. And they're announcing some changes in policy. And the Florida Lottery Secretary resigned. We can't take, she had other scandals. It wasn't just this scandal. But it is nonetheless true. And then there were arrests and jail time for the ticket aggregation as well as other violations. It turns out a few people did go to jail for ticket aggregation, but not many. But a more common outcome would be that when law enforcement goes to investigate with a search warrant and they look at the premises, they have found in many cases evidence of more serious and more easily prosecutable crimes. And so as a consequence, they turn up things. So lots of stuff happened. So in summary, just to recap, the theorems, real theorems surface shenanigans. And some of those are criminal shenanigans. And that spurred changes nationwide in state level policy and caused a bunch of lawsuits. Well, that's maybe not a positive outcome. And law enforcement actions, which will hopefully improve the environment for the future. And also the shenanigans are pretty widespread. There's probably hijinks in your personal state. Every state has its own lottery games with their own little quirks. Every state has its own enforcement apparatus, which has its own little blind spots. And every state has its own little underground subculture, which may be coming up with its own crazy hijinks. So there's probably something weird going on in your state that doesn't quite fit in the boxes we've talked about that you can analyze too. So, and if you have questions about IDA, come by the Big Career Center this afternoon. Thank you very much.
Well, I see people are departing for lunch. Skip is standing here all alone. So if you have questions, I propose you come up and bother him right now.
Thanks.
Well, I have a question.